This is a continuation of our notes on simple harmonic motion and waves. We know that lots of objects in our world move back and forth repetitively along the same path over and over and over and over. And a common example is the pendulum of a grandfather clock. The pendulum hangs down, and if we pull it to one side from the center position and we release, it'll move back and forth like this. The dotted line shows the center position of the pendulum's repetitive path. And when the pendulum moves like this, we say it oscillates, which simply means to swing back and forth about a center position. When there's no friction, we call this type of oscillatory motion simple harmonic motion. And since we're learning so much about new terms, here's one more. The pendulum itself we can call a simple harmonic oscillator. So pretty simple so far, right? You might be thinking that this is just one random example. What else oscillates in simple harmonic motion? Well, as it turns out, tons of things. Things as simple as a guitar string, to the speakers on your computer, to the atoms in an oxygen molecule. You can even test simple harmonic motion in your own home with a rubber ducky in a bathtub. Fill the bathtub with water and let the water be still. Drop the ducky into the still water, and the ducky will bob up and down in simple harmonic motion. But not everything that moves back and forth is in simple harmonic motion. For an object to be in simple harmonic motion, it must follow this equation. In fact, when we say the very words, the rubber ducky is in simple harmonic motion, what we really mean is that the ducky's net force is equal to the opposite of a constant times the rubber ducky's displacement from the water surface. So any object that meets this equation is in simple harmonic motion. We call this the defining equation for simple harmonic motion. Now, as it turns out, this equation for simple harmonic motion isn't so simple. It has some important implications. Any object following this equation will have three characteristics. First, the object will move back and forth repeatedly on the same path, like we've already been seeing. So let's look at the pendulum again. If we pull it to one side and we release, then the frictionless pendulum will continue swinging back and forth along this circular arc, like this. So this back and forth repeated motion is actually a consequence of this equation. Number two, no matter where the object is momentarily located along its fixed path, the net force on the object will always pull the object back to its center position. So if we have a pendulum and it's up and to the right of its center position like this, the net force pulls back down, so that when the pendulum is at its center position, it's right here. And if the pendulum is up and to the left of the center position, here's the center position where I'm circling, the net force will pull back toward the center position. Number three, when an object's displacement or position changes by some factor, some proportion, then the net force changes in the exact same way by the exact same factor. Here's an example. If our pendulum is over here, let's say it feels a net force of 10 newtons. If we cut the displacement in half, so that the pendulum is half as close to the center position, the net force is also cut in half, or divided by 2. But the pendulum, the rubber ducky, and everything else I've mentioned isn't even the simplest example of simple harmonic motion. Next, we'll return back to the spring and Hooke's law. Let's display a couple of equations that we'll be using a little bit later. Here's the equation for simple harmonic motion, and here's the equation, Hooke's law. Take a horizontal spring and attach a block to the end. What happens if we pull this block, we grab it, and we pull it to the right from its center position, which is shown with a dotted line? If we pull it to the right, our hand will be exerting a rightward force, and the block will pull back to the left. There will also be gravity and the normal force, which balance each other out. Now, if we're holding this block at rest, then clearly the net force is 0 and the block doesn't have a net force, which meets the defining equation for simple harmonic motion. So the stationary block fails to satisfy this requirement, and it's not in simple harmonic motion. Intuitively, this makes sense because a zero net force cannot restore this block back to its center position, and a zero net force can't cause the block to be moving back and forth in simple harmonic motion. But what if we let the block go? Now, there's not going to be the force of the hand pulling the block to the right. All we'll have is gravity and the normal force, which balance, and then there will be this spring force, which is unbalanced. So the net force on the block will equal the spring force. And the spring force, we know, is equal to minus kx, so we can replace the right side with minus kx. Compare the released block, right? This released block, compare its net force to the equation for simple harmonic motion. They match. And so this block will be in simple harmonic motion, and it will be pulled back by the net force to the center position. But if the block is in simple harmonic motion, it should be moving back and forth along a fixed path. Is that what happens when we let go? To answer this question, we're going to look at a really nice simulation provided by myphysicslab.com. Here's a horizontal block attached to, here's the block attached to a horizontal spring. The block is currently at rest, so it's at the center position, which is about right here. If I click on the block to grab it, and I move it to the right, we said that if we let go, the block will be in simple harmonic motion, and it'll feel a net force equal to minus a constant times the displacement. And that means that if I let go, the block should oscillate back and forth about the center position. Let's watch what happens. Clearly, the block is moving back and forth along the same fixed path, and the center position is right where it started, about here. So yes, we can see with our own eyes that this block is in simple harmonic motion. Now, before we move back to simple harmonic motion, and before we look at the last example of simple harmonic motion, we have to learn about something fun called the small angle approximation. The small angle approximation says that at really small angles, the sine of theta approximately equals theta itself, the angle. This only holds at small angles, and for it to be true, we have to measure the angle theta in radians, not degrees. You may not believe that this is true, which is why I've prepared a nifty little chart. Take a look at theta equal to 0.05 radians. The sine of 0.05 radians is 0.05. That's about a 3-degree angle. Even down here at 0.20 radians, that's a 12-degree angle, about 12 degrees. The sine of 0.20 is 0.199. That's less than a percent error of 1%, less than 1% error. And even down here at about a 23-degree angle, the sine of 0.40 is 0.389, which is only a percent error of 2.7%. So this is a really helpful approximation that we'll be using later. But back to simple harmonic motion. Besides a block attached to a spring, we're only going to see one more example of simple harmonic motion in detail. And you guessed it, it's the simple pendulum, our old friend. But when we pull a simple pendulum back, we describe how far it's been displaced as an angle theta. This is called the angular displacement. And it's okay to use angular displacement here because the equation for simple harmonic motion is really powerful and it applies to all displacements, not just left-right displacement. It even applies to angular displacement, which means that in this equation, we can simply replace x, the left-right displacement, with theta, the angle that the pendulum is displaced. Now, let's find the net force on this pendulum and prove that the pendulum satisfies this equation for simple harmonic motion. We know that gravity pulls the displaced pendulum straight down like this. The force of the rope, or the tension, supports the pendulum up at an angle like this. Now, I'm going to draw in a tilted y-axis and a tilted x-axis. Since the gravity force is at an angle to the axes, and it doesn't lie on any one of the axes, we can break it into components that do lie on the axes. There will be a tilted x component, and there will be a tilted y component, and these components form a right triangle. And in the right triangle, the hypotenuse is this, the thing at the angle, FG. We call that R. But what's theta? To answer that question, we're going to use a little geometry. Because this is straight down and FG is straight down, we have parallel lines here. That means that this angle right here at top, this angle, is equal to this angle. And because this is pointed along the tilted y-axis, and this is the tilted y-axis itself, these two lines are also parallel. And that means that this angle here is equal to this angle. So what we can see is by looking at this right triangle, FGX is opposite the angle theta. Thus, FGX is R, the hypotenuse, times the sine of theta. Now, the hard part is finished. Let's clean up our picture a little bit. We can take away theta, and we could slide FGY over to the axis so that it's stemming from the pendulum itself. When we have a small angle, the gravity force roughly, and the last thing to say, because we've represented the gravity force with its components, we can remove the gravity force from our picture so that we only represent it once. Now, at small angles, the tension and FGY roughly cancel each other. And that leaves FGX as the only unbalanced force on the pendulum. In other words, the net force on the pendulum is negative FGX. The negative sign is there because FGX points along the negative direction of our tilted axis. But FGX is equal to FG sine theta. That's what the box shows. So we can replace FGX with mg sine theta, like this. And now, here's the magic. Remember that the small angle approximation says that the sine of theta is replaceable with theta itself at small angles. So we can take sine theta and replace it with theta. And at small angles, the net force is approximately equal to negative mg times theta. But mass doesn't change. The pendulum's mass doesn't change. And g is always 9.81, which means we can rewrite mg as a constant. And look at this. We've just finished our proof. What we've just done is we've shown that the frictionless pendulum has a net force which satisfies this requirement for simple harmonic motion. And instead of a spring force, the force that restores the pendulum back to the center position is FGX, the tilted y component of the gravity force.